One division uses a variety of techniques to mimic the classic multi-camera setup of old-school sitcoms, but if you're a video nerd like me, you might have noticed something which gives away the fact that they're using a modern cinema camera instead of a TV camera. It's especially visible in this shot here, the blurred out background. You almost never see this in low-budget TV, but it's very common in movies. The reason has to do with the size of the sensor used to capture the image. So first, let's define what we're actually talking about here. When you focus a camera lens, there's only ever one infinitely thin plane which is exactly in focus at any given time. The farther away from that plane an object is, the more blurry it will be. Additionally, blurred objects will often show these bokeh orbs, which are technically present everywhere, but are particularly noticeable with bright points of light. However, the rate at which faraway objects become blurred varies depending on the lens and the camera being used. This is called the depth of field of the system. If you use a setup with a deep depth of field, objects that are out of focus will still be relatively sharp, and bokeh orbs will be quite small or non-existent. Whereas on setups with a shallow depth of field, there is only one thin slice of space that is sharp, while everything else quickly loses its definition. Which is better depends on your needs, but in many cases a shallow depth of field is desirable because it helps draw the viewer's eye to the subject. So how do we achieve a shallow depth of field? Well, there are a number of different factors which influence it, but for the moment, let's just take a look at one: focal length. The focal length of a lens is a property in millimeters which influences the field of view that you get out of that lens. As you increase the focal length, your field of view gets narrower. And if you pay close attention, you'll notice that something else happens as well. As focal length increases, the depth of field will get shallower. And here's the crucial thing: this relationship is not linear. We aren't just zooming in on the bokeh that was there before. The bokeh actually gets larger with the square of our focal length. To compare side by side, on the left is an image captured with a 35mm focal length and digitally zoomed in 200%. And on the right we have an image captured with a 70mm focal length. The field of view between these two is the same, but the 70mm image has a much shallower depth of field. Zooming in 2 times, we would expect the bokeh to be twice as large, but it's actually 4 times as large. So, going back to our original question, what does this have to do with sensor size? Well, let's look at what happens if we use the same lens on a camera with a larger sensor. In this case, our sensor is 1.5 times larger, so our field of view is 1.5 times wider as well, even though our focal length is the same. But we don't want a wider field of view. We want to achieve the same perspective on a larger sensor. In order to do this, we need to increase the focal length of our lens by 1.5 times. So watch what happens as we move from 35mm to 50mm. As you can see, the field of view on the large sensor is now the same as the one on the small sensor, and yet the depth of field on the large sensor is shallower. You can think of it like this: switching to a large sensor made the bokeh smaller by a factor of 1.5, but then zooming back in to the same field of view made the bokeh larger by 1.5 squared. So the end result is a depth of field which is 1.5 times as shallow on the full frame sensor compared to the Super 35 sensor. Now, you might be wondering, couldn't the small sensor just open its aperture up wider? Well, yes, to a point. Another factor which influences depth of field is the f number of the lens. This basically controls how wide the aperture opens up. Reducing the f number of the lens opens up the aperture and makes the depth of field shallower. So if our Super 35 camera reduces the f number of the lens by 1.5 times, it compensates for the shorter focal length and achieves the same depth of field as the full frame camera. So yes, theoretically it's possible to achieve any depth of field on any size sensor, but past a certain point, the f number required to achieve a particular depth of field becomes incredibly impractical. In the earlier example, our full-frame lens was at f4, so it was easy to match by opening up to f2.8. However, what if our full-frame camera was using a much faster lens, say f1.4? In that case, the Super 35 camera would need an f.93 lens. And if you know anything about lenses, it's that as the f number gets lower, the price gets higher, exponentially so. In general, large sensor cameras use longer focal lengths to achieve the same field of view. So they're able to achieve a shallower depth of field with much more practical and affordable lenses than their small sensor counterparts. In this example, the difference in sensor size was only a factor of 1.5, but comparing modern large format cameras to an old TV camera, the difference is more like 3 times. That's why you hardly ever see a shallow depth of field on low budget TV. They're using cameras with smaller sensors, but their lenses aren't really any faster. And that's how we can tell that WandaVision wasn't filmed with classic TV cameras, and instead used a much more powerful Arri Alexa LF. To be clear, I'm not hating on WandaVision. I actually really like the attention to detail they put into the cinematography and the editing, and they probably made the right call anyway, since they still need to deliver in 4K for streaming, but it's just a little thing I noticed. Anyways, I hope you all enjoyed this video. My name is Cayman Crocker, signing off.